Today, we're going to start our bridge design series, session 8. This session is the last one for this year. And the session 9, we're going to start new year in 2022. So the till the others join, I'm going to start the session. I think that today what we are planning to do, we're going to discuss the assignment I gave it to you. I don't know how many of you have tried this one. If you can solve this assignment, the question I asked is much bigger than your charter report, or even if you can solve this one, I think it should be you can be a really good bridge engineer. And the first couple of slides, I leave it as it is for legal reasons, and then the format of the presentation, I just bit updated from the previous one. I think it's make more sense. Today we're going to discuss about the bridge assignment, and then the next year, then we're going to have a year and break. Then next year we're going to start the new session. So I will give you the assignment number 2. That's also to do with more calculations related thing. Yeah, then the bridge modeling part, I thought of getting to bit more detail into that. Because of that, I split that one into 2 parts. Another thing I thought of concentrating to focus this one to finish within 2 hours time. So bridge design, we're going to go for 2 sessions as well. Then we're going to discuss the bridge assignment 2. Then the rest. So today's session, I'm going to give you a summary between session 1 to 7. You will find out why I'm going to refresh your memories, because what you have learned so far, you need to solve this problem. Within an hour and a half time, I can't solve this problem, complete solution, but I will guide you. I will guide you how to work around yourself. I think this assignment, I encourage you to do it yourself or with the team. And yeah, because the same one I'm going to use to do the bridge modeling as well. And please remember, this is one of the real problem you're going to solve. It's a real problem. It's combined this session, what I call the concept bridge design, is combined with the feasibility studies as well. Combine them together. What we try to understand, try to achieve in this session, understand the constraint when you are designing a bridge. And if you have already read this one, it's nothing is in there. It's a piece of, it's a document there. There is a sketch for the alignment. And that is what you get when you start from the scratch. Then how to develop a bridge geometry. That's the first thing you should do. This is a lot of input is coming from road engineers. Then we select the bridge types. I gave you, I explain you many, you will see them. And then we select the bridge substructure type, then bridge solution, then understand the construction and other issues related to your solution, then associated risk, understand the cost benefit and value for money, and select the bridge option. I'm not sure within 2 hours kind of a time I would be able to run through everything, but the document I prepared today, you can see a lot of slides there. If you download the slides I sent to you, but yeah, I try to focus this one as much as possible. Let's see, but I want you to try it yourself. So then I'm going to refresh your memory. This is really quick and really fast, The session 1 was the introductory session. I introduced you to the stakeholders in the bridge design. You are not doing it alone. You are working in a big team. And then as a bridge engineer, you need to focus on the durability of the structure. You could remember a lot of aspects. We saw that one. Durability is one of the key elements, because your structures, you have to design according to Euro standard 420 years, for other standard like Australian standard 400 years. Then you have to pay a lot of attention. I just touch base with that one. And then when you're designing things, now in the modern trend in the world, the safety is one of the key prominent key areas you need to deal with. And then I introduce you to many different bridge types, because I'm refreshing your memories, all this knowledge you need to solve this assignment. A lot of bridge types I introduced. I just put a one slide. If you go back and see, there are many type of bridges I introduced. I gave you what is the span range, what is the depth range, what is the width, what is the slab thickness, and even the number of strand, and even this the dimension of the spans, and different articulation, bridge articulation type. Or I explain you different type of expansion going to be used. And then in the session 2, if I introduce session 2, we discuss about elements and their performance. This one started with this diagram, this Ramanine bridge. What are the skeleton of a bridge? We divide the bridge into superstructure, substructure, and foundation. We call the substructure superstructure link is the bearing that led the bridge to articulate. So then we notice what are the elements in the superstructure: deck, beams, barriers, and joints. And then substructure: cross heads, cross beam, column, abutment, wing wall, etc. And the foundation, of course, you all quite familiar with footing and piles. Then I introduce you to a different type of bridges. This is the Ramanine Expressway, 15-kilometer long bridge. I explained it to you, the difficulties we had this during the construction, using the cast in situ slab with very difficult formwork, and we changed the design. So these are the things you should know when you are doing your assignment today. And I gave you this example, and there are some pros and cons we discussed in that presentation. In addition to that, explain it to you, if you are building bridges in a urbanized environment, steel is one of the ideal solution. But in terms of durability, that is not the best. But anyway, steel bridges are quite common for flyovers and the bridges for not short span, because I used to build bridges as long as 3 kilometer long using steel. And then I talk about the quite complex kind of a bridges, like a Panankau bridge. We got the continuous box girded bridges, where the bridge superstructure and substructure combined together. There is no bearing in this one. You got a deck, you got a column, you got a footing. That's the whole bridge. And I talk about this. We use the ground conditions, soft ground. We use the flexibility in the bridge to achieve to get the expansion joint across and distribute the load along the length of the bridge. Then I introduced this slide in there to other small structures in there, the abutment structures, batters, then the link between the bridge structure and the road pavement or the batter. That's the connect by the abutment with the approach slab. Then in this area, there is a level difference because of the structural dimensions. We talk about how we're going to work around in here. Then I explain it to you, depend on the ground condition to achieve the differential settlement. Sometimes the approach structure can be as long as 100 meters. Like if you do the construction in Bangkok, you have here, for example, if you build a bridge in the Muthurajavela or in a subsoil area, these abutment structures, we call this the structures, we call the transition structures, bearing unit, different names designers call it. It could be as long as 100 meters to get the the settlement around in here is about 15 to 20 millimeter against the, depending on the ground condition, you may have a long-term differential settlement up to 200 to 300 millimeters, even more. So therefore, the bridge abutment design on that one is the combined exercise between the structural engineers and geotechnical engineers to get the right outcome. Otherwise, the asset owners will have a lot of issues during the service period. This is one of the typical abutment structure we use for in the good ground, because in this structure we support the bridge, and then that structure should be able to attach the approach slab. Therefore, we need to have a wing wall on the top. One in the approach slab is on the top to get this level difference. The different approach slab thickness 350, the thickness of this girder and the abutment is about 2 meters or 1.7, I should say. Then to get this level difference, make it, then you need to have a wall and to retain this soil behind, otherwise soil will become here seepage through this wall. You need to have a concrete element. That's what we call the abutment curtain wall. I beg your pardon, I say wing wall, it's not right, curtain wall. We need to put this one in here. This is how this structure look like. And then this dimension is not coming from structural relation. This dimension is coming from geometric reason. That is what you're going to see it in your assignment today. And depend on the expansion joint type you saw in your articulation lecture. If you use a finger plate joint in this particular drawing, the picture you can see is a finger plate joint. The water will come through this one. Then you need to have a bucket to collect this water. These are minute detail, but it's really required to get the performance right. Otherwise, if you use just a standard one, you can use the spill through the batter elevation. Show it in here. The batter normally is stable if you have it, if you have a 2-to-1 batter in the abutment structure. Then I introduced you to many different bridge types. I gave you the requirement, what are the lengths you can use particular, and how you're going to select them. What are the constraint requirements, the limitations, everything I gave it to you. These are the important element. You need to use it when you develop, solve this assignment. Yeah, that's the whole idea. I gave you this assignment to refresh your refresh your memory, and then go back and grab the information and use it in a proper way. Then I introduced you to the segmental, the box girder kind of a bridges. They can span economical if you can span more than 40, because these bridges, I girder bridges, it's not economical. You can't span them beyond 40 meters. It's really hard. Then we go to box girder type bridges. And then as I explain it to you, the cost differential is significantly large, but still if you bridge a long bridges with different constraints, sometimes this bridge construction cost may be, there's no significant difference compared to I-girder bridges. And then I talk about many bridge types when I explain it to you. When you build the bridges, like a flyover bridges, you see we got expansion joint in the every pier, but to avoid that one, we use the link slab system. The link slab, there's a limitation where you can push your expansion joint distance with the link slab. The calculation is based on the creep shrinkage and the thermal deformation in the bridge. So you need to use that knowledge to solve your design problem in that assignment. So then I gave you the typical link slab detail. I explained it to you. One, this is the standard one we use in Australia, but the other one I use it the different substructure type. I explain it to you without there's a big gap in here, without having this girder supporting the link slab with the debonding. You can have a link slab across the structure like. Then the number 3, I think we talk about more or less bridge design principle. I think any structural engineer familiar with this one. But to start with that one, I said when we were designing bridges, these are the situation we need to do. The clearances, the earthquake, and failure due to wind. I think in the last lecture, you all familiar with that one, and then earthquake, flooding, and ship collision, the construction, during construction, the collapse. All these things could happen when you are constructing a bridge. There are heavy longitudinal center structures. Because of that, you need to familiar with those things. And then I discussed this one in detail. When you design the bridge, the philosophy is it should serve the purpose, should be fit for the purpose, the functional requirement. Not only that, should be aesthetically pleasing, should be buildable, should be maintainable, it should be sustainable. I think today the sustainability is one of the key things. If I may remind you, I think I gave you the example. For example, in New Zealand, the government decided to use the timber as a as a construction material instead of using concrete and steel, considering the sustainability requirement. So in addition to that, the other engineering principles you need to, what sort of engineering principle you need to use when you are designing this one. And then the safety and performance requirement we discuss, and then we discuss over there the durability or design life, the limit state, the ultimate limit state or serviceability limit state designs, and how we're going to apply different situations. Because when you are designing, like when you learn things in the university, or when you are in your practicing, you use the ULS, SLS, they always you work with the around factors, but when you are designing a bridges, you work around the environmental loading, like a wind, earthquake, and flood. Then we talk about the return period, the probability of exceedance. So that's where we work around. Then analysis method, linear and nonlinear. I haven't go into detail in this area, but during the bridge modeling, I'm going to discuss a bit in detail. I think the external, the design actions we talk about a lot, and then how we're going to verify the design. I think this thing we didn't do calculation, but in philosophical terms we understood. I think the last lecture you all had a good understanding about wind and earthquake, how we're going to incorporate in the in the design principle, not exactly directly into the bridge, but how we're going to apply in a structure. Then safety in design, sustainability, and then I gave you some example. If you not properly designed, if you not consider your sustainability requirement, and then the climate change, another thing, the flood effect, and if you are not SID, not properly consider the failure like this, and then if you not properly design it, the durability aspect. So this all costs a lot of money, and then to repair you need material and a lot of resources. So that's what you need to be really concerned about this thing. Then the section, the session 4 and 5, what I did, I'll summarize the, we went into detail about the loading. It's almost, we spent close to 8 hours in there, talk about loading. Then we knew what are the loading on the bridges subjected to. The main, the primary load we designed the bridges is for the traffic load. That is really unpredictable. It could be a small bicycle load to a massive truck as large as few hundred, like a close to few 100-ton weight of trucks moving on the bridge. You had to design to that range, and then how we're going to deal with that one. And then we talk about the bridges are long and slender, very heavy structures, dead load. In addition to that, we put what we call the superimposed dead load. After we place the deck, after the bridge becoming composite, we apply the load on top of that, like a wearing course, barriers, and light improved drainage, and all miscellaneous stuff on the bridge deck. we call superimposed dead load, like a wearing surface. For example, you put 70 millimeter thick wearing course, but over the time, 10-15 years later, it will be reduced to 30-40 mm. Then you have to resurface. So then, in addition to that, we talk about the bridges subjected to earthquake, floods, and winds, and then how we need to deal with them, how we're going to estimate them. Then the bridge loading I categorize into 3 categories: permanent effect, transient effect, thermal effect. The transient effect is the time-dependent one, is go and is move in and out, like a traffic, the main thing, an earthquake, water flow, wind, and then the impact, collision, etc. And then the permanent effect, there's a time-dependent load, what we call the creep shrinkage. We looked at that one in detail. So the thermal effect is quite key because the bridges are long and slender structures. The temperature variation got a significant impact on that one. I think I promise you guys, I'm going to give you how to calculate the differential temperature in a cross section. It is still due. I haven't forgot that. I will do that one. I will put that one in this the course in the resource folder later on. Yeah. And then I separate the loads into the superstructure and identify gravity load, longitudinal load, and lateral load. Why longitudinal load? When you are driving on a bridge, you brake. So that one, and the creep shrinkage, thermal, there's a longitudinal effect on the bridge. And then the lateral load, of course, wind, and the centrifugal effect, seismic impact, etc. And this I explained you in detail. I think you can go back to this slide, so you can go back and re-listen to the recorded session. So then I went on to explain about substructure loading as well. And the lateral load is quite significant in the substructures, especially the seismic, waterfall, collision, etc. And the earth pressure, lie load surcharge, explain them in detail, how we're going to evaluate them even. Yeah. Then everything we get there, we categorize again the loading to understand better, to combine them together, to design the bridge. We categorize A, B, C, D, E, F, G, H, I, J, K, A permanent load, and then the traffic load. Then the F is the flood load, G is the earth pressure load, K is the wing load, and H is the earthquake. And then when we design the bridge, we say in the red, we primarily design for the rail, the traffic load and the permanent load. Then we check for the others. That's how we design the bridges, because otherwise some people design the bridges for earthquake loading and check for the traffic loading. That's not the right approach. And then we said the earth pressure and thermal is always go together with the permanent effect. Your bridge always subjected to earth pressure together with the loading. In addition to that, the thermal loading is a bridge is moving in and out all the time. So I explain it to you how to get the bridge models, the different load models, how you're going to get, how you're going to evaluate them, different combinations. I explain it to you why when you have a 3-truck, you don't use all these 3 truck. They are percentage 100%, because the probabilistically this when we're using the lie load, we use the lie load models. Those models are much heavier. For example, in the Australian standard M1600 load, that means if I just say in word 25 meter length, it weighed like 160 ton. And in terms of in the Euro code LM1 loading, you apply in here 27 kilonewton per meter line load within your lane with 600 kilonewton tandem in here. They are really heavy. The probability that all these load interacting with each other is less. Different code, different approaches we discuss. I explain it to you in detail. Then in addition to that, I explain it to you how we're going to place them in the bridge when we were designing them. And these things very important. Next couple of sessions when you're going to go into in-depth in bridge modeling and analysis and the designing, how we're going to place them and how you're going to get your design outcome and design the members. Then these effects we combine, we separate them to what we call the serviceability limit state, SLS, ultimate limit state, the way the bridge, the load factors they were using in different code in a different way. In addition to that, I forgot to mention, when we were working on the bridge designs, what we did, we talk about dynamic amplifications requirement, but in Euro code is already included, but in the other code like Australian standard and then the ASHTO and then Canadian standard, you need to multiply your model using the dynamic load allowance as well, or dynamic magnification. Then I explain it to you, the original slide, the permanent effect, transient effect, thermal effect, how we're going to combine them together in our SLS serviceability limit state. The load effects, you can remember I explained it to you, why superimpose dead load. We use a 1 point factor. The factor 3 is not 1. The reason is the bearing course. You keep overlaying. There is no control. You can't control that one. Therefore, there is a risk. That's why it's multiplied by 30% instead of all other most of other load factors. For the serviceability limit state, we multiply by factor 1. So then when we go to the ULS load combination, these factors, the way we have two different ones. One is we increase the factor by 1.2 and then we multiply this factor by 0.85. I think this the amplification of the load factor 1.2 is you increase the load, but the reduction is more to do with the way you estimate your dead load, for example, densities, and there are variability in here to take that one into account. You make the 0.85 when you reduce the self weight. If there's an earthquake and then uplift from the structure, that's going to govern the design. So therefore you have to look at in your design, especially when you check your pile for tension, you need to use this load combination. So I explained this one in detail. This information is quite important when you're going to do bridge modeling and the other thing. But today assignment, we're not going to go to that extent, because if I hate to go to that extent, I need to spend with you at least 7 to 8 hours. So then this session 6, I talk about bridge articulation. That is one of the common thing. As I mentioned before, your substructure is here, your superstructure is here, your substructure is here. It's connected by the simple element called bearing that will allow to your bridge to move. I explain it to is like your joint ligament in here, because that's allowed your not only allowed to bridge to move, again it's transfer the load from superstructure to substructure. But the way we are going to use is the very simple small element. I think if you listen to the Professor Pennon lecture last the session 7, he talked about the earthquake. One solution, they use the elastomeric bearing to isolate the bridge, the building and the foundation, and he show you some model and the actual behaviors. Yeah, you can see if you design a bridge with the elastomeric bearing, low bridge, like we say, I explained it to you, the expansion joint distance could be as long as 300 meters. So if your bridge is sitting on the elastomeric bearing, in the earthquake situation, the earthquake generates from the ground, the substructure is moving. Because it's sitting on the elastomeric bearing, you could see that one, the superstructure movement will be significantly less because of the damping effect of this bearing. The effect will be make it less. So therefore, this eye girder bridges sitting with the bearing in terms of the earthquake is a good design. So I think we talk about that one, and then we went into detail how we're going to accommodate this one. I think this is the right one, because the structures are quite long, subject to their pre-stress or post-tension. Mostly at the beginning and the very first day when you do the pre-stress, it's got a camber going upward. When you erect that one, sitting on the bearing because of the self-weight, and over the time, it's going to go down with the deflection. When you pour the deck, it's further push the deflection downward. And then there's a support movement in the bridge because bridges are sitting on soft ground, and on the ground plus on the soft element like rubber bearings. And then there could be a differential settlement. In addition to that, braking, thermal expansion, contraction, bridges move in and out in the longitudinal direction. In addition to that, the flexible structures, like especially if we use steel girders, it will be very flexible. They will be rotating. Yeah, you could experience this one if you are sitting, especially in a flyover bridges in Bangkok. You will be going up and down in the flyovers. Even if you use the flexible box girders, especially the steel, they will be rotating, and there will be the rotation in the cross section, the twisting. All those things combined together, you get the effect on the bridge. That we're going to translate through what we call the the rubber bearing pad, or what we call, we introduce the larger bearing, pod bearing. I think I explained it to you. Pod bearing, there are the pod bearing, one is sliding free, it allows the rotation. Another one is the guided one. It's guide you like you're driving your car in one direction. Another one is fixed. It is not allowed to move, but it's allowed to rotate. So then if you can't work with the pod bearing, then you can go to spherical bearing. I gave you one classic example, the spherical bearing, the industrial ring road project, and that 1,800 ton gantry we operate. So these are the examples I gave you. And then the way we articulate the bridge, we categorize the bridge: floating bridges, then the integral bridges, semi-integral bridges, and that sort of thing. I clearly indicate you, explain you the behavior of the floating bridges, integral bridges, and semi-integral bridges. And those behaviors I thought of explaining to you all during the session too, but later on I changed my mind, and then I push back to make sure that you have a better understanding about you get more information about the bridge, then you can easily understand that one. I think I went this thing in detail. I spent that lecture as well 4 hours. I want you all to just refresh your memory. Then only you can work on this one. Yeah. Now the last 30 minutes I explain it to you. I talk about almost 18 hours. Yeah. Close to 18 hours I spent with you. I think it should be more than that, not less than that. I just summarized within 30 minutes. I should have done that one even 15 minutes. Yeah, because this is the thing. I just refresh your memories, and then you got slides, you got this YouTube link. If you think if I missed something in here, you need to go back and refresh. And if you not understand, you can write back to me, then I can explain it to you. So then today, now I'm going to explain it to you. Sorry, excuse me. Bridge assignment. This is called bridge assignment because I gave as assignment, but this is actually a bridge concept design development. It's not feasibility. This is the concept design. The reason I said the concept design, we going to come out with bridge solution. According to this assignment, I'm asking you to develop, I think, 8 bridges. I'm asking you to develop 8 bridge solutions and pick 3 and recommend that one to client. With the time, I'm going to stop the lecture. I'll try to finish this one 2 hours time. I'm not going to go much into detail. This is the actual problem. This is the real problem. This is a real problem we solved about 10 years ago. I should say maybe more than 10, it's about 10 years ago. You have seen a lot of pictures, that particular problem, the actual bridge we design and build is in service. We have seen those pictures as well. what is this question asked? Part of the extension of the existing motorway, road agency, let's say RDA, has asked your company to develop concept designs option for a bridge across the valley as shown in the sketch. I hope all of you have this bridge assignment handy in your hand. Yeah, a printout. What is concept design? The concept design is the one, when you design the bridge design, we go with the few stages. One is the feasibility studies. You just go there and see, this is, I want to put a bridge, what sort of thing, whether I can do it, what sort of information we know, we call REF, a review for environmental factors. I think different countries use different names. And for example, utilities, geotechnical investigation, heritage, environmental impact, and all those things we're going to review. And we develop that one, all these things, we develop a report, and that report we submit to a company and ask them to develop the concept design. The concept designs, it could be many. And then you make concepts, you estimate what sort of budget you need to build this particular project. If you are a very good contractor, when they go to the site, they know from the sketches, we know the area of the bridge, we know the structural dimensions and things. From the concrete volume, they can tell you exactly the price. But road agencies, they can't do that one. There are a lot of risks, a lot of things they need to consider. Because of that, they ask the designers to develop concepts. The concept design is not one option. You need to present to your client many different options. Then they can see, they can weigh every option, pros and cons, yeah, the risk and things. They all convert that one into, at the end of the day, you have to put a price tag onto the risk. They put Monte Carlo simulation, though so many risk assessment, they get the price. That is the purpose of developing the concept design. But the concept design is the bridge. Not exactly they're going to build, but this bridge should be able to build. You will give them the dimensions of the deck, your girder sizes, slab sizes, cross girder sizes, column sizes, foundation, everything you give them. That's what I said. If you send it to the estimator, they can price it straight away, assuming certain amount of percentage of reinforcement. Even now, the current requirement, the client say, I want the price. That price for this concept design with some contingency, it's like it's about it's vary from country to country. It's about 40 to 50%. From your price you estimated, they put 40 to 50%. In addition to that, the management cost and things, another 30, 40%. They get the budget. This budget, yeah, you know, whatever the government agencies do, they need to get the money from the government. That means the treasury. Treasury need to get the approval from the parliament to the project. That is the process is come, or else is allocated to your ministry. There's approval process. Then at the end of the day, the people, those who are approving things, they are not engineers, they are not bridge engineers. They always see there's a bridge. The purpose of building this one, for example, reduce the accident, to make it this motorway more efficient, or because we have a business entities, we want to develop that area. The commercial purposes, we are building this one. Then they see how much you're going to invest, what is your rate of return of investment, ROI. They compare that one, they approve the project. This is how it goes. But for us, what we are going to do, we do the initial work, and that's what we try to do in here. This is a real problem. I modify this problem to a little bit for you to work. The question is the bridge should be, the vertical gradient is given. Yeah, this is the initial state. This thing can change later if need. Horizontal alignment is given because we know there are 2 points to connect. We know the way we need to connect it. And then the bridge length approximately given, or they said the bridge length has to be 420 meters. They said it has to be longer than that, should not be shorter than that, because the bridge construction are costly, the road construction are cheaper compared to the bridge construction. Therefore, if you not give that limit, what the designers can do, you can just keep reducing the length of the bridge. You can fill up that one. There are reasons to do that one. I'm not going to discuss this thing in detail. This is the problem. So this, what is, and then the, I'm going to this figure. This is the valley. They're going to build this bridge in this valley. This is the slope of the bridge. This drawing is not on scale. The bridge starting at the abutment A, I put the station 0, abutment B, where the bridge minimum length distance is 420 meters. Is the station, is the length. Then there are constraints in this bridge. This is the valley. There's a creek running in the middle, in the bottom section of the valley. The width of the creek is 30 meters. For environmental requirement, you can't go and touch this creek. You can do things, but you can't build your structures within the creek. Whatever you build, it should be outside. In addition to that, they say in the future, they want to put the slip lane going in front of this abutment, because to connecting ramp, like a slip road, connecting two places, one place, another place, we need a slip road. Like, for example, you want to connect two suburbs on either side of the bridge, this highway. So you want to connect that one, you want to have a slip road. So these are the thing, when you're designing your bridge, you need to keep that one in your mind. Nothing can be done within the creek, but in this area, you need to make provision to build another road in front of here. You need to assume there is a road when you are designing this abutment. There is a road always going in front of this one. So then the question I asked, I gave the constraint requirements as I explained before, and the geometric requirements given, and the bridge should be supported on the board pile. You can't go back and work on a spread footing. I never recommend bridge to be built on unless otherwise it's a competent rock to be built on pad footing. You can assume the confident rock. I gave that one if you want to just use in your bridge modeling. Later, we're going to use the same problem for bridge modeling purposes, 5 to 15 meters below the ground level, for you to assume the bridge height and get imagine the flexibility of the bridge. The design should be considered the whole of life cost. What is whole of life cost? Is the bridge should be not cheapest bridge. From the design to the construction to the maintenance to the dismantle or decommissioning of the structure, the overall cost and the purpose, the value for money. You build the bridge, after you build 1 year later is a bumpy road, like a bumpy road is bang, bang, bang all the time you are driving. No, that is not what our expectation. And this bridge built in an area, the people are living in a community area, in a valley. And I said the driving experience should be the pleasant experience. All those things need to be addressed. That is how whole of life cost will be addressed in the design. This is not the price tag itself. Please remember, the people happiness, you can't put a price to that one. So yeah, you can't put the price to that one. Yeah, the number 4, design must ensure that driving through this valley should be a pleasant experience for road users, right? Yeah, that you need to ensure, but with the optimum cost, the maximum benefit. That's the whole of life cost. You must provide at least 4 reasons to justify. You are developing 8 solutions. When you are presenting to client 3 options, you need to sell the client why these options are good. You have to put the pros and cons. Yeah. Unfortunately, I don't have a time to go through this one. That's what I said to you. You get together as a group, develop this one. So if you are a junior team of engineers, you can get the advice from your senior engineers. They can help you out how you're going to deal with step 1 to step 2. Or if you all work together, then another way you can do, if you 3 or 4 people work in this one, then you can have a Zoom session with me, like a half an hour discussion. You can send me the question I can answer, you can explain it to you. I can clear your doubt. Yeah, please try to do this one, because this assignment is going to continue throughout this series. Yeah. This bridge you're going to design at the end of the day. We're going to design detail, find the rebars, find the bearing, and you going to do everything, but you need to do the step one, right? You remember, to me, I never consider as a designers if you are just number crunchers, right? That's why I never do in the, I haven't done any calculation with you yet, right? You need to understand what you are going to do first. So then we know what is it now. So first thing we need to do, geometric requirement. Before you design the bridge, they gave you this bridge, the levels they give you, right? You can see this ground levels is 19.8. This is 25.6. This looks like a 7 meters above. This is 25.6. This is 9 meters, right? It's going to 38.2. We just crunch the numbers: 25, 38, 63, 64 divided by 32. Here 32, here is 9. The level difference is 23 meters. Level difference here is 23 meters. I said competent rock is about 5 to 15 meters below. The competent rock is 10 meters below. 23 plus 10. The height is 33 meters below. This bridge is cantilever, 33 meters. This bridge cantilever here, 33 meters. When you look at the bridge cantilever height in here, it's much less. If you see this bridge, if you draw this one on a scale, then this bridge looks complicated. Yeah. That's why I gave those data for you to imagine. Yeah. For you to get your the basic things. Why am I getting my messages? Anyway, then we know the bridge height, we know the length, but we need to design we need to first calculate what is the size of the width of the bridge. Without that, you can't do anything. For that, we gave the geometric requirement. They said this bridge, the lane width is 3.5. That is quite standard. And the first part, I said, we need to have a dual carriageway, each carriageway carrying 3 lanes. I hope you all read the assignment. You got that one in your hand. The part 1, we're going to look at 6-lane bridge, dual carriageway, 3 lane each way, southbound, northbound, let's say. You got a 3 lane. Each lane is 3.5. When you are building a bridge, dual carriageway, then carriageway you need to separate from each other in the center, what we call the median barrier. We provide the median barrier. Then, you know, your bridge is building up in the air about 23 meters above the ground level, then you need to have an exterior barrier to contain the vehicle. So we already learned that one. So then you got an exterior barrier, interior barrier. When we were driving on the structure, the road design requirement, you need to have a, according to side distance, the design speed, you need to have a shoulders. There are 2 types of shoulders. One is the outer shoulder, the other one is inner shoulder. The outer shoulder is 1.2. This is in the edge. The inner one is the median, close to the median barrier, that is 0.5. So these data is given. The shoulder with inner, outer given, lane width given, the barrier width given, all this given. So then you can calculate what is the width of the bridge to accommodate all those things. Any question here? You can calculate the bridge width, right? You agree with me or not? The question is the information given to you. Can you calculate the width of the bridge deck? Someone say yes or no, please. To me, I can. I'm just asking from you, please. So no answer means yes. Is that right? Okay, then. I can't hear you, Sampath. Yeah.
Yes, we can, sir.
Okay, thank you. Then, when we calculate the bridge, the width with that data, I think this slide should have been on the other one. Anyway, it doesn't matter. The bridge, yeah, I'm really sorry. This slide should have been before the previous one. The bridge geometry, talk about this and bridge with vertical alignment, horizontal alignment. Beg your pardon, you should excuse me. And then the bridge skewness, I will explain a bit. The classic example in here, this is the motorway. You want to build an overpass in here above this motorway, linking this side and the other side. You can see when you place this girders, the bridge piers, you can't put them perpendicular to the bridge control line. The ideal one is putting perpendicular to the bridge control line. Sometimes you have to orientation of your bridge substructure should be parallel to the motorway. Yeah, because otherwise, when you are driving, you are driving this way, you see a bridge is going across. You feel awkward, right? Even if there's you need a really big area to have that one as well. So because of that, most of the time when we are building, when you are putting your substructures in the piers, we have to locate them parallel to the existing motorway control line or to the traffic, and that creates the skew. That skew angles will lead to sometime when the selection of the bridges, sometime the extent of the analysis we're going to do, we have to keep that one in the mind. That's why the bridge skew angle is quite important. And I put that one, I say the performance requirement. For example, there's a limitation. If you put the very torsionally stiff the girders to build bridges, this eye girder, this skew angle have an effect, especially during construction. You might get a lot of cracks and other things. Yeah. Then, if I go back to this one, when the bridge geometry, first we're going to calculate the width of the bridge. Yeah, this is your bridge. You got a 3-lane. Because in the first exercise, we're going to design the dual carriageway, that the combined carriageway, separated by median barrier. I got a 3-lane. You can see I put that one in 3 different colors. You got 6 lanes. Outer shoulders, inner shoulders. You can see this table, number of lanes, lane width is 3.5, number is 6. That total 21 meters. Then outer shoulders, there are 2 outer shoulders always. Yeah, because edge barriers. Then width is 1.2. This the road designers will give you. Yeah, 1.2. It could be as long as 2.5 or 3 meter if you use this one as a shared user path, more than that. So then this 1.2, we don't allow people to walk or ride a bicycle in here. 1.2, and then the 1.2 in the sense this alignment is more or less a straight as well. Then 1.2, number of the outer shoulders is 2, that works out then 2.4. You got the inner shoulders. Width is 1.5 meters, and then we got a 2, that's 1 meters. You got a median barrier. The median barrier thickness is about 680 millimeters. I make it a round figure, 0.7. And 0.7, only 1 median barrier. In here, that's 0.7. We got a 2 exterior barriers. I think I gave you a lot of bridge drawing before. This one, to get the deck, I put this one 0.5. That figure also a little bit changed, depending on the shape and urban design and stuff like that. The 0.5 is reasonable for concept design. There are 2 edge barriers or exterior barrier, edge barrier, you can name it. Then you calculate this one together. The width of the bridge is Dual carriageway width is 26.1 meters. Then this total length here to here is 26.1 meters. In other words, when you are constructing your bridge deck, the deck width should be 26.1 meters. When you are designing your bridge, spanning across in that length, it should be able to support 26.1 meters with deck. It carried 6 traffic lanes. Yeah, it's going in both directions. So we know the width of the deck for dual carriageway. Similarly, I calculate for single carriageway. This is not divided by 2. That's what I want to show you. We do the same exercise. If you are designing a bridge, use the same format, do the same calculation, understand yourself, draw this picture. No need to draw in AutoCAD, draw a line. Yeah, use a color marker, make it like the kindergarten kids are doing. That's the better way to do it. So then 3 lane, because the single carriageway, because what's the single carriageway is going to do, we're going to replace this median barrier using a H barrier or exterior barrier. That's how we're going to do. The same thing is in here, right? We're going to replace it with H barrier. So 3 lanes are there. We got outer shoulders, only 1, not 2. Why we not going to put 2? The reason is still there is another carriageway in here. It's not going to, any structure in here is not going to topple, fall down, right? Because there is another, the carriageway on the other side in the same level. Only thing, they are separated. So because of that, we have only 1 outer shoulder, and we got a 1 inner shoulder here. We don't have a median barrier. That's what I put in 0 here. But instead, we have a 2 exterior barrier. This is the width of your single carriageway. So there are 2 of them. You need to keep some gap between these 2, like a 50 mm or 100 mm. Here, you can make it. And when you put 2 the individual carriageway independently, 13.2 times 2, 26.4 plus the gap 10, then your total width, the occupied the bridge, will be 26.5 meters. Is 400 mm wider than this one. Okay, I'm not going to discuss this one in detail. That's I'll let you to do. Now I know my bridge width. I know whether it's single carriageway or dual carriageway combined together. I know what is my deck width. Then next one, I know. Then I had to select type of a structure. First, I need to select superstructure. Then to match with that one, a substructure. To support that one, I need a foundation, right? Depending on the type of the structure I'm choosing to articulate, I need to select type of bearing. Depending on the length of my bridge, I need to select appropriate expansion joint. That's the only thing you need to do. That's the only thing you need to do. Let's see the step 2. We're going to say what sort of bridge structures we're going to use it. The reason I put all these pictures in here today, then easy for me to show it to you. Yeah, you can have this type of structures. You can have this type of structure, right? You can select any type of bridge when you are selecting today in your work. But in my design, I'm going to discuss with you the simple type of bridges. That's day to day, every day, we're going to design. I'm going to select my bridge superstructure as a beam slab type superstructure. Yeah. And my substructure, of course, substructure, whatever section you select. Yeah, it could be a portal frame structure, it could be a single column. Yeah, it's depend on your superstructure. Substructure will automatically dictate superstructure will dictate the form of substructure. Then if I'm going to select beam type, beams slab type structure like shown in this drawing, I girder or super T girder. I explain it to you, load transfer mechanism. The load is because we space the girders as space apart. Then load first goes to deck, go to deck, to the bearing, to the headstock, to the column, to the footing, to the pile, to the soil. So if you are going to select slab beam type structure, in your bridge, you have all these items. You can see in this picture, deck, beam, you got a bearing, you can see headstock, column, you can see the foundation. Foundation you can see in here, you got everything in there. Then if you say, no, I don't like that one, I want to use the wider box girder like a Fanankao bridge. The box is 27.6. It's a twin cell single box. You can still design, right? If you are choosing a box, then you can replace your deck and girder with one unit, a box. Then your column and headstock, sometimes you can replace with a column. The bearing, of course, you need. The footing and pile, if you need, you can combine. So then your structural element you need to build and select is less. Box, column, bearing, box, bearing, column, and the pile. So then if you go to other type of bridge, is a single structure, twin cell box girder bridge. You can build this one as a continuous, even bearing you can eliminate. Only box, only column, only the foundation. You can see you have a lot of choices to make. This bridge is 420 meters. Even you can propose a cable stay bridge. You can propose a balanced cantilever bridge. I want you to propose all sort of bridge. I don't give you the information to cable stay bridges. Yeah, even myself, I haven't designed those things. And I learn about myself, but I involve with a lot of stuff, but haven't designed myself. And I don't want to give you those information, but I gave you information regarding how to come up with balanced cantilever solution. I want you to try all these solutions. Today, I'm going to discuss with the beam slab type. I'm going to give you, I will give the guidance. Use the same principle, you can use it. I gave you a lot of information to select this. The box type bridges, I gave you a lot of box girder solutions in your reference. I think I gave you American Society of instead of segmental box girder bridge manual, I put that one in the resource folder. Everything is there. You just need to pick. Yeah, and you need to select to match with your requirement. And then when we're going to select, as I mentioned, select bridge type, select the bridge type, we're going to select the bridge with the beam slab type bridge. So there are few kinds. The girder, you need to select type of girder. It could be I girder, it could be a bulb T girder, could be a super T girder. So I'm going to go with the bulb T girders. One is for the safety reason, especially the constructability reason, because we are building this one in a valley. The reason why I select that option in here, sorry, I don't have a slide in here, because if you just go with the I girder, there is a gap after you erect this one. When you are filling this gap, the formwork, when you place in that, temporary formwork is really hard to do there because the height of the valley, 23 meters maximum. It's vary from like a 9 meter to 23 and again to 5-6 meters on the other side, in the abutment B side. Because of that, it's too risky and too costly. Because of that, I'm going to go with the bulb T-type girders because it provides you the formwork, the working platform already. When you erect the girder, you can walk on the top. Even Super T, you can do the same. Then if you select your girder type, well, all three these girders I need to mention to you, you can span quite the same length. You can span quite same length. And if I select this one, you have a reason. That is what you need to explain to your client. Okay, that's the one reason. He will ask, why didn't you select I girder instead of bulb T girder? Because I girder is lighter, easy to transport, easy to erect. The bulb T girder, because you are putting this slab on the top, then you are adding additional weight. You are adding additional weight. So that weight, difficult to transport, difficult to erect, sometimes it's not 100% contribute to your bridge deck, because this thing will be acting like a more or less a formwork. You're putting extra money in here. Why are you going to do that? So you need to have a reason to the client, because safety first. And this valley, you can't build this one. The construction cost is higher. If you get your temporary form, how you going to support this one? It's in a valley in this slope. How you going to work? You need to put this argument in front of in here. You need to justify your answer. You don't have a justification to select the bridge width, because that's the given. You have to follow that. That's a requirement. But in here, you are selecting, you need to justify. We have a justification in here. Of course, the slab thickness is 200, quite obvious. I advise you, please never design a bridge less than deck thickness, less than 200. It's very difficult to build. Yeah, it's difficult to build. You can't get your concrete covers and hog and other thing. Because of that, keep the slab thickness minimum to 200. That's a standard design around the world. Yeah. And then we select the girder. We know the slab thickness. We need to calculate number of girders for this 26.1 meter wide bridge deck. That's what we try to do now. So then we're going to go with the girder. The girder depth I select in this bridge 1.8 and 1.5. Okay, you can ask me, Rohita, why didn't you select 1 meter spacing, right? If you select 1 meter, or why didn't you select a plank bridge in here, right? I can put a lot of planks in here. Planks are cheaper, easy to build, very easy to transport, erect and everything, right? You need to understand you have to put so many substructures in that valley. It's really difficult to build, right? So you need to get the balance. So then 1.8 meter girder and 1.5 meter is the common type in this range. I want to say this one, for example, in the different countries, 1.8 may translate into 1.7, 1.5 may translate into 1.6 or 1.4, right? Yeah, and then the girder is 1.8, then slab is 200, because when you are building a bridge, we always use the slab and girder acting together like a composite unit. Therefore, in our design, when you put the lie load, the girder depth is not 1.8 meters, the girder depth is 2 meters. So then the total depth of the girder is 2. Then we are building eye girders using simply supported beam, right? Every girder end we have a 2 bearing. So these are simply supported. Because of that, these eye girders behave like a simply supported bridge. Then the maximum span, the span is L over 20. Your depth is 2, then 2 times 20 is maximum span 40 and 34. Sometimes these are already with the guidelines. You can find it. Then the H distance I gave there, I think I will just go to this one. The H distance of the girder, I gave this distance, center line of the bearing to the back end of the girder. This we need for, if I just put a simple word, to force transfer mechanism to strut tie model, you just need this extension in here, the minimum 450. And when you place the other girder, because this bridge is not single span, many span, even single span, there's always gap. This gap in here, then combine them together, 450 plus the gap 50 millimeter, then you get total 500 millimeter or 0.1, 0.5. So then if your span is in the girder is 40 meters, when you add the end distances, your girder length for 1.81 is 41 meters. Then for 1.5 meter deep one, 35 meters. So now you get your span length. For 1.8 deep girder, I can have a 41 meter span deck. If I go to 1.5, I can go to maximum 35 meter deck. Then you get a 420 meters. You split, divide this one into 41 and see how many span you need. Or divided by 35, you see how many span you need, right? And if you know your bridge span, then you can calculate your bridge span arrangement. If you know the number of span, that means you know the center line of each and every substructure. You know how many substructures we need to build. Of course, we need abutment A and B. In between, how many that's need. That's how you're going to calculate it. I just want to ask from you, up to now, do you have any questions? I didn't do any calculation. Now I already finished 40% of your concept design. Yeah, because now I already select this bridge girder because they are built in. These girders are more or less quite similar because they, yeah. And I have this, the other dimension, everything fixed. Yeah. And you have your girder, you have your bridge deck, you know your the span arrangement, and then you know your number of girders, then you need to calculate. Any questions up to now? No? Okay. Then we calculate the girder spacing or number of girders, right? Again, I want to apologize. I think this slide should have been before the other one. We know the bridge width, the number of girders, the way we normally calculate the I girder construction. If you go to steel, you can go to the large spacing, but the concrete I mentioned is between the economic, the better one between 1.9 and 2.4. Yeah, we'll start like a 2.1 meter spacing. The number of girders I need to get is 12.43. We don't use girders 12.43. Then we have to select closest figure, the 12. I use 12. The reason is dual carriageway. There are two sides. 12 mean even number, 6 on this side, 6 on the other side, 6 on northbound, 6 on southbound. If you use select 2, then you have to modify your spacing. If you divide your width by 12, you get the girder spacing 2.18. Girder spacing 2.18. And then I said, okay, I get to try. I want to reduce the girder spacing further down. Then I increase the spacing close to 2.4. I go to maximum 2.3. Then I increase the girder spacing to 2.3. I can see number of girders required for the bridge to support this 26.1 meter width. And the number of girders required is 11.35. Should be a round figure. We select 11. then girder spacing is 2.37. This is quite close to 2.4 meter. If it is a super T girder, of course, is ideal. Even I girders you can design with that. Yeah. Then now you need to select. Are you going to put 11 girders or 12 girders? Yeah, then your friend might say, come on, if you put less girders, it's cheaper, right? Lesser the number of girder, lesser the number of bearing, the cost should be less. It won't work that way all the time. Yeah, please, yeah, remember, yeah. In this case, they are quite close. It might work, but it's not. When you are selecting this thing, you need to look at the other aspects. The girder weight. What is the weight of girder if you use the 1.8, 1.5, the space in 2.18, 2.37? What is the weight of the girder, right? How difficult to fabricate this girder? How the efficiency, fabrication, erection, transportation? Heavier the girder, you need larger vehicles. Sometimes there are routes it's not allow you to transport. If your route is not allow you to transport 70-ton girder, so with the weight of the truck, it should be 100 ton, then you don't have a choice. You have to reduce your girder weight. Fabrication, transportation, erection, and the cost. Because heavier the girder, you need the larger machinery to lift. So then, when you are doing this one, if you do not have experience, you need to talk to people involved in the industry and talk to them. Yeah, and need to get their information. At least you need to talk to people, have some knowledge about them, get their advice. These are the stuff you need to put in your, like, when you are developing the concept, the reasons you did this one. Another thing, the wider the girder, the stability, especially the eye girder, when you erect, it's not safe. In the bridge, in a higher elevation, if you put the eye girder, they will twist, even in the wind, rotate. You need to have a lot of temporary bracing. Your stability you need to consider. And the construction staging as well, you need to check. There are so many factors you need to check when you are selecting your girder. I again apologize because this slide should have been discussed before that one. So you select your span, you select number of girders, then you need to select the span arrangement. Any questions up to now, please? Is it clear or is it confused? Please, someone need to speak because please remember, I'm just talking to your computer. You are sitting with next to your friends at least. Huh? Can someone answer me like up to here? Because we calculate the bridge width, we select, we're going to discuss at the first option, the beam slab type bridge. Then we're going to look at 1.8 and 1.5 meter girder. That is quite common in the industry. We want to look at these two options. Then we looked at that one. Then we need to calculate the number of girder. Now we already did, right? We already did this one, mean you already designed your superstructure. Am I right? Right? Your superstructure consists of the girders and the deck. Because deck is already 200, right? The barrier already standard. So your superstructure is complete. Then you need to go to your substructure. First, you need to know how many substructures I need to put. So that is decided, that will decide by the girder span. It's quite obvious. It's quite obvious. Longer the span, lesser the number of substructures. That's yeah, it's quite obvious. And after we calculate all this girder, number of girder spacing, we come up with the the bulb T girder solution. This is a standard solution. I just put this one in there. And if you would like to go with Super T, you can replace the same thing with the Super T. Yeah, 1.5, 1.9. You can do either way. Yeah. But when you present to the client the solution, you can't put one solution Super T, another one bulb T girder. It doesn't make much sense, but you can do, but both are more or less the same. Yeah. Any question up to now?
I have one question.
Yeah.
How the magnitude of the gradient of the vertical profile affect for selecting the type of structure?
I think it's not going to affect that much actually, Sampath. The reason is the bridges when we design for like a fixed, like a predefined speed, like let's say motorways 100 kilometers per hour, at least 80 kilometers per hour. The vertical gradient is actually a geometric design to get the side distance depend on the vehicle speed. There are limitations in that one. Yeah. Superstructure selection is not going to affect that much when we are selecting the girder type. But if he has to put this bridge in a skew angle, yeah, like this skew angle limit, for example, you can put the Super T girder bridge if a skew angle is more than 35 degrees. In that case, you have to go to more flexible. Super T is torsionally stiff. It's kind of a box compared to I girder. Then you have to go to the I girder. It's torsionally more flexible. Yeah. That the way the geometry is forming. In other words, like if you have a curve girder, then the sharp horizontal curve, then sometimes you have to design with the box girder to accommodate that torsional effect. Did I answer?
Yes,
Did
sir.
I?
Yes, sir. Thank you, sir.
Okay. And then we design our superstructure. And then we're going to select our substructure. Okay. When you are going to select your substructure, we already know our span length, maximum 41 and 35. We're going to play around with that. But please remember, there is a creek right in the middle of this, not right in the middle, in this valley, in the bottom part of the valley, you got a creek, 30-meter width. That's a requirement, environmental REF requirement. You can't put any column or you can't put your structures within the creek. Whatever you build, it needs to be outside this 30-meter clearance zone, right? So then you need to make sure that your span arrangement is not going to encroach in here. That is the one of the constraint. You need to keep this one in the mind. From the abutment A to the distance is 230, and abutment B to the creek is 160. You can put column anywhere in here, not in here. Okay. First, you don't want to worry too much about this creek. You would first assume there is no creek. I'm going to select this span arrangement. I'm going to do an initial estimate. There is nothing in there. I can put whatever I want between this abutment A and abutment B. That's my assumption. I put the same numbers again. Girder depth 1.8. Then our maximum span 40. The length of the girder 41. You can see in this figure. Span is here. Then the length of the girder 41. That means this center line to the other center line is 41 meters. For 1.8 deep girders, 1.5 is becoming 35 meters. So the number of spans I need, very simple. The length of the bridge minimum, because we are working, we don't want to have a 450 meter long bridge when they need 420, right? And first we divided 420 by 41. Then you got a span 10.24. So therefore one can say I put 41 meter 10 span, I put 0.24. It's about like this is a 20% of that value. is about 10 meters. I put the last span 10 meters. Yeah, it's job done, right? 41 into 10 is 40, 410. The last span 10 meter, I'm going to have that one. What's wrong with that? Yeah, of course, it's a bridge. 10 meter also span with the bridge. I'm not going to use I-gird or anything. I'm going to put a plank in there. I just cross that one. Yeah, there's a solution. Yeah, of course you can. But there's a word we call value for money. When you are designing a bridge, there's a requirement is that we aesthetically placing. Therefore, you need to come up with the solution make sense. Like when people look at this bridge, when they were walk underneath valley, when they look at this bridge, say, okay, this makes sense, looks beautiful. People would like to go under this bridge, not like go somewhere there, say there's another tunnel going underneath, going to get shocked. So because of that, we're not going to go into that solution, right? Because 10.24 meters, I can't go to 10 meters. Why? If I go to 10 meter, a number of span to 10, sorry, number of span to 10, the span length become 42, then it's more than my maximum span. So therefore, I need to increase this number to the nearest next number is 10.2 for me, 11. If I have 11 span in this one, then the span length is becoming design girdle length, including this gap, 38.18. But this one is divided 35 divided by 420, you get 12. That one hasn't changed. So you can see 1.8 meter deep girder, 48.41 meter, all of a sudden 41 meter length reduced to 38 meters here. So that's by about 2.2 meters. Then I'm not worried about anything in this valley. I just calculate my span arrangement, right? The abutment A, my station is 0. It's just arithmetic. You add 38.1, this is the station 1. Another 38.1 is station 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11. 419.98, that is 420, right? This is the 11 span arrangement. The location of the span, my girder. So if you go to this valley, sorry, I just, if you go to this valley, you can draw this line in here. If you draw this line, you can calculate your vertical height. You can do everything. I assume you have this paper with you in your hand. And then I do the same thing for 35 because it's got a 12 span. Yeah, they are not coincide with each other. I put the same table, 35, 70, 105, 140, 175, 110, 245, 280, 315 goes to 12 span. We know our column position. Then no problem. We go back and yeah, finish the span arrangement. You already done. Have you? No, I don't think so. Why? Because we have a constraint. We said we can't put any column. It can't encroach into the creek. We know from abutment A, 230 meters away, we have a 30-meter wide creek. 229, one must argue that 229 is the center line is 1 meters away. Therefore, it is not in the creek. Yeah. No, because you need to understand your column got a width, your foundation got a width. Because of that, this is too risky. But if you see the next span is 267.6. The creek, the station start 230, the end 260. In this one, the span or the pier number 7 is stay away from the creek. But this is too close. If you go to 1.5 meter span, no problem. that is right in the middle of the creek. Right in the middle of the creek. Therefore, this solution is not acceptable. The 1.8 meter deep solution, one is quite close to the creek. If I put the foundation, it's encroached the creek. Therefore, this is not acceptable. We need to go back and change it. And the other one right in the middle. Here, right in the middle of the creek. You can see the 38.1 meter, 1.38 meter, 1.8 meter deep girder, you have a flexibility to ship whole thing. There's a big gap in here. You can ship this one here. But this one, ship half a span is not that easy. Then the concept has to be, this one need to be built aside. You need to have a span, one pier on this side, one pier on this side. Then you need to get your bridge to work. This you can't just do in an Excel sheet. You can do this one only if you draw in a piece of paper. If you draw in a piece of paper, work out that way. Yeah. And then considering this one, I know this one, I'm going to push this one this way. Then automatically this one will move that way, right? Towards abutment A. I'm going to push my span arrangement towards abutment A. The way I'm going to do, I'll separate my bridge into two segments, one between the abutment A and the creek, and the other one abutment B and the creek, in the sense of creek embankment in either side. So then, when I rearrange my arrangement, what should I need to do? This 38 meter span, I'm going to reduce. If you reduce the length of girder here, right? Because we can reduce this girder and we can increase the girder. We don't have a problem. If you reduce this length of the girder here, this 29, the pier 6 will move towards abutment B, then that will stay away from the creek. But it can, there's plenty of space, this can move this way. Then the problem solved. So that's how, what I did. What I did, I changed the span before the creek, I reduced to by one. Yeah, you can play around this one, 37.6 feet. Then other side, I increased to compensate because you reduce the bridge, you move the bridge in here, then you have to stretch a bit to the other side. Then I stretch the other side. You can see 38.2, I will put a round figure, 38.2, I make it to 37.6, I reduce 600. And you have a 6 span or 7 span, then 4.2 meters you shift in here. You lost that 4.2 meter, but you need to accommodate within 5 span. So then I increase 38.2 to 38.9 meters. Then I got my span arrangement. So then this one, 230 and 260. Yeah, you got a 5 meters and 4 meters clearance from the face of the creek. So therefore, this solution is okay. Pier will locate more than 4 meters from the creek, sufficient space for foundation, span arrangement is okay. More flexibility to arrange the span by varying the girder length. 2 spans arrangement are given. You see, I came up with my bridge solution. There are only 2 types of girders I have, the lengthwise. You see, you are multiplying this number. There are 1, 2, 3, 4, 6. 6 into 11 or 12, then you get that number because the number of girder multiplying. Because every span we got 11 or 12 girders. So then 1.8 meter solution is fixed, right? But as I mentioned before, this one in here, the only way to do, put one in here, put one in other. in a symmetrical way. Because the creek is 35 meters, you need to have at least 2 to 3 meter clearance to build this bridge foundation and the column. Because of that, I opt to use 35 meter span over the creek. 35 meter span over the creek, and change the span, creek and the abutment A and the other side. So my span I changed 32.5 before the creek and 35 meter over the creek. That is what I have to do. 31.5 meter other side of the creek. You see this creek make your life a bit difficult. Your design, you have that constraint, make this design is difficult. So then you can see there's a 2.5 meter clearance is there to work. It's really difficult, but it's possible. The span arrangement is okay, not much room to play across the creek. 3 different girder lengths are in here. Because it's 35, the maximum one against 31.5, 32.5. The girder weight have some difference, even the erection, the place in there will be the issue, but still the solution is possible. Now, you know your span arrangement, that means you know your pier positions. If you come up with the substructure form in the dimensions, then you can design you can come up with your bridge solution. So then you got 1.8 meter deep. The number of span is 11. I go with the girder space in 2.8 mean, number of girder 12, then you need 132 girders. The same as if you reduce the girder depth, the number of span is 13, number of girders 12, is girder 156. If you just calculate this value, you can't just calculate number of girders, you need to, the only way you can say look at the tonnage, the weight of this, what is the ton, how many ton of this girder and that girder. Yeah, the comparison you can make is, yeah. And it's not the straightforward one, okay? I just need to say there are so many factors affecting to get this cost right? But these solutions are possible. The span arrangement is possible. The girder can be fabricated. It can be transported, unless otherwise there is issues you can't transport that weight, right? It can be erected. Yeah, it's depend on the availability of the crane, especially if you are working in Asia. This heavy crane is very expensive, but if you work in like in Australia, the comparatively heavy crane are not that expensive. It's readily available. And then if you go to the girder, the wider girder, we reduce the span to 11. You can see you get a 121 and 143 for 1.5 deep girder. If you go to two extremes in here, 1.5 meter deep girder, you can go up to 151, but 1.8 meter girder, you can go to 121. You can see your design solution have upper bound and lower bound solution, right? But the cost factor, if you see, it may sometimes go other way around. When you number of girder optimization, this is the best solution. But in terms of cost, it may not be the ideal solution, but you can present this one to your client. In your options, you can say, I got this option, but still within that, you have a range you can look at in the next step. Or you can ask your estimators or the company you hire to do your costing to look at all these options here. It's already got 4 options in here, not one. 4 design options in one solution. Yeah, 4 different bridges. They are not the same. 2 span arrangement are the same, and the 2 different superstructure arrangement, number of girders, 11 and 12. So you got your substructure location, but you don't know yet your substructure. And you will ask the question, we haven't done any analysis. We got our girders, we got our shapes. And how do I get my the substructure without doing any analysis? Yeah, still we can do. Still we can do. I will show you how you're going to get your substructure form. Before that, I want to ask you any questions up to here. Yeah. You are almost there with your bridge design now. Any question up to here?
So one more.
Yes.
So one more clarification. In the bridge alignment data you gave, the abutment A is located at the station 100. Then the abutment B is located at the station 420. I thought that the bridge length is through 320.
Oh, sorry, it should be 0.
Okay.
Yeah. Sorry, I think yeah, it should be 0. I put the length of the bridge 420 on the top. Yeah. Sorry about that. Thanks for pointing out that one. Thank you. Thanks. Okay, then I will jump into the next slide. We got the span arrangement. We know exactly where we're going to locate this one. So in your piece of paper, sorry, I didn't draw this one because I had to draw each and every line in the blue beam as stake ages. Yeah, that's what I didn't draw that one, but you can draw yourself later on. Yeah, if someone can volunteer, they can develop this one in AutoCAD actually. Everything, elevations are given, levels are given, locations are given. Yeah, and then when you know the location, you can calculate the column height, everything. You can do that one. So then we're going to select substructure. Because we're going to have a one bridge, 26.1 meter width. We have an individual girder, 11 or 12. And then 11 or 12 sitting on bearing. Then the substructure is quite obvious, it's a portal frame. You can see this picture. This is this bridge I talk about in the same valley we built. Yeah. This exact same problem you are solving, you can see in this picture. Yeah. It's not exactly the same, but it's different. Yeah. So the structural form is a portal frame, simple. It's not complicated like building. You see, bridge design is pretty easy compared to building another thing. The architect involved, I will show it to you, but very not up to a lot of extent. Yeah, you can, when you're looking at this bridge itself, you can see there should be an architect in here. Yeah, you will see that one, the next couple of slides. So we got a cross set, we got a column, footing, pipe. We can even replace the footing with the pipe. Yeah. Then we see how we're going to decide these dimensions. How we're going to decide these dimensions. The cross set. The cross set dimension, whether you like it or not, is dictated by a different parameters. When you are placing the bridge, because this bridge is continuous, it's got a 11 span or 13 span, right? So then we place the two girders aside. When you place the girder, it's heavy, right? Sitting on the bearing, there is a significantly large pressure in here. If you do not have a sufficient distance in here, this concrete will crack. And if a bearing is warped, the bridge will slip. During an earthquake and other condition, there should be a space. If a bridge is slipped, it should not be come down. So there are so many reasons because of that, and the size of the bearing itself, they are not small. Remember the example I talked about during the bridge articulation. The standard side of this bearing is the 480 by 380. The width is 480, the length is 380. So then this distance and the distance between these two is already given, because this end distance we need. That's 450, the gap is 100. Then you got this dimension B, 2 times edge distance plus gap, that is 1000 millimeters or 1 meter. This distance in the standard practice 500 mm or 550. It's depend on the size of your bearing. Some people push this one really hard to 450, 400, but sometimes it's really hard when you come to design, especially they neglect, you get the reinforcement stirrup here. When you bend the stirrup, you get a 4 time diameter radius in here. They neglect that one. Because of that, some bridges, you got a crack in the concrete in here. Yeah, so you can't see this stuff. You need to realize you build this bridge, how many meters above the ground? You build this bridge 20 plus meters above the ground. Yeah, nobody can see it. You just go and inspect that bearing or going to replace. Yeah, once in a blue moon, like couple of years time, you go and see that one. Because of that, you need to keep that one in the mind. So when you calculate the crosshead width, it's come 2A plus B is 2 meters. Yeah, 2A plus B, 2 meters. So then you know the width of the crosshead. When you are working with architects, they don't let you to do, because I need to jump in from here. They don't let you to reduce the width of this column in here. They don't like it. They want flush surfaces. They want real flush. They don't like kink surfaces. Even in terms of the design performance, it's not good. This is the good, especially earthquake design and detailing. You don't want kink in here. Even in terms of the force transfer mechanism, because they are heavily loaded structures, it's very hard to design this thing. Not easy to design. So the width of the column and the width of the cross beam is the same. If you would like to reduce this dimension, you can do in different way. So what I try to say now, without doing any calculation, you get your width of the cross beam. You get your width of the thickness of the, not the width, thickness of the column. So in your portal frame, you know the width that into the page and the thickness into the page. So you just need to calculate what is the depth of the cross girder. For that, you need to do analysis. For that, you need to do analysis, or you have to use your past experience. The column dimensions more or less is same. When you play with the architect, if the thickness is T, we should be at least 2T. Yeah. Or as 1.8 something T. You can't go and, yeah, otherwise T and T. Otherwise it should be square. It should be tapered, nice way. You can play around many different ways. And if you don't like a flush cross set, this is quite common in Asia as well. I think I explained this link slab in the when I was talking in the before. Eye girder you place here, you put your link slab over there, you support in a corbel. This design construction is really difficult, and the yeah, it's not the preferred option. We use this option only where in the urban areas, if you use to reduce the clearances, but it's not the preferred option to me. But still, you can use this one. Yeah, this headstock is quite wide. It's about 4 meter plus. Yeah, you can still use this one. Or else you get your cross girder width 2 meters, you need on the top to support your girder. But if you want to reduce the column size, using 2 meter column too thick, too much concrete, you have to look at the cost, the whole of life cost, sustainability thing. And even the thicker the concrete, casting is really hard because of thicker the concrete. When you pour that one, the differential temperature effect, you need to have a lot of other mixed design and controlling requirement during construction. Then you can save a lot of cost plus the time, formwork and so many things. So you can reduce this one to reasonable size, 1.5. So the way you're going to do, as I mentioned before, when you work with architect, they don't let you to have a king, so you need to taper this one down. The smooth surface, yeah. Then architectural placing, you can have this shape. Yeah. Someone can argue, I want to have this rectangle because it's cheap. I can convince my architect to accept that one. My client is happy, I want to go that option, is fine with that one. Yeah, fine with that. There is no argument in there. Yeah. Now you know your column dimension, then the foundation could be with the footing with 1.2 meter diameter piles. Yeah, that is your bridge. This depth you need to calculate. You need to use your experience. You need to put your girder location. You can use simple calculation to get the girder reactions, or else you can run a grillage model. You can run a simple bridge model. We do in the concept design stage. You can calculate this one. If you want to estimate the cost, you need to give your estimator the steel per cubic meter. You can estimate that. If you get your load in, you can do that one. Yeah. So in the concept stage, when you go to concept design stage, you don't know your dimension in your grillage, your model, your 3D model. You know your thickness of the column. Yeah. Because you are not dealing with the architect, you may be 2 here, 2 can go here. Those things, those member sizes, you can change later on in your final model when you run and when you decide everything. So on this one, the solution is the end here. We get the minimum dimension to match with the cantilever one, because if you get this one same depth, this look not nice appearance wise. You can see this big photo, right? To get the blend with the bridge and the dimension, yeah, this height and depth and everything is dictated by the architects. This cantilever length, yeah, dictated by the designers, is quite significant. It's 5.1 meters. The center line between the piers in the portal frame is 16 plus meters. Yeah, this one you need to decide from a model, from the design. If you get this design, this is your concept for the bridge. You can build this without footing, because this structure is more flexible. As I mentioned, your rock is about 20 meters below the ground. You can have a flexible structure. Because of that, you can have a single pile without footing. You can save money in your footing. Yeah, these are the pictures. This valley during construction of similar bridge. The early stage, you can see a picture. It's a valley. You can see still the bush around in here. It's the urbanized area actually. You can't see the sun. It's up in the hill. And then I'm going to tell you, because this bridge design, you haven't finished yet. You need to put the expansion joint. As I mentioned to you before, I think I put that slides in this presentation today. I passed that one. This kind of a bridge, you can go up to 260, 270 meters without any problem with the link slab. So then we can locate our expansion joint. You can push around here. There is no harm. If I go to span arrangement table, you can go to 188 or you can go to 225. Either way, it's the same. Because I select this one, this one, because that's the edge of the creek. And the difference between the both sides is not significant. So I put my expansion joint at PS6 in 1.8 and in the PS6 in, it should not be PS6, it should be PS7. Please, please change that one. Please update your, yeah, should be PS7, sorry. I forgot to edit that one. Sorry about that. In the PS7, you can see this length more or less the same. Your expansion joint, I put a note here. If you go to bridge articulation, I have this table. You can't put the strip seal joint, that's the cheapest. That can accommodate only 125 millimeter. You have to put the finger plate kind of a joint that can accommodate up to 600 mm. This kind of a bridge doesn't have that movement, much less than 600. If you put the finger plate joint, you got a problem. What is that problem? Because this bridge is in a 3% slope. During rain, the water is going to this one. You need to have a drainage gutter running underneath this. Then you need to have a big gap between your girder. This thing you need to edit, you need to change because you are doing concept design. Don't worry about that. The only thing in this particular place, instead of having 2 meter wide, 2 meter wide cross set, you need to have a wider cross set. You need to have a wider cross set. Why? You need to have a space to put a bucket here, 300-400 millimeter wide bucket. So that means this 2 meter, it would be 2.3 or 2.4. Yeah. In this location, in this bridge, you need to modify this particular pier. It's going to impact your column. It's going to impact everything. When you change this dimension, it's going to impact everything. So you have to change this one. This is one thing. It's not standard. Colombo, the design is common because this cross section is typical, except the location of the AJ. Yeah, the reason I put this bridge, the one we already built, we didn't have this bridge is shorter. We avoid this one because of this change. But in this particular case, it's difficult to avoid. But we can design with the extreme ends. We can go to extreme ends and we can design this one, but it's too risky to do that one. And to avoid the one special pier in the center, you don't want to change a lot of things to avoid that one. Yeah, it's not worth. Yeah, and I mentioned here the way you're going to calculate this one. Deformation of the bridge using creep shrinkage. I think if you're using a Euro code, you can calculate the creep shrinkage. You remember I gave you an example last time. The creep shrinkage calculation, you cast your bridge deck, right? You loaded everything. When you are setting expansion joint, this sort of bridge construction will take about 1.5 years. So your creep shrinkage, the date you are calculating, 1.5 years after you put everything, loaded the deck, or 1 year or 6 months at least, from the 6 months to 30 years. So that make a significant difference in your residual creep and shrinkage value. Thermal expansion contraction, easy to calculate. It's like a floating structure. Yeah, that is the L divided by 2, L alpha T divided by 2, this one. Expansion or contraction. You will see in the modeling, when you apply the break-in load, the bridge will be more like a rigid body. Then the deformation is a function of the bearing stiffness. Yeah, I think you could, this well explained in the last presentation actually, Professor Pennon. And then the using the shear deformation of the shear stiffness in the bearing, you can easily calculate what is the deformation of this, the deformation due to breaking load. That is good enough at this stage. Even when you apply that one in the model, you can calculate. You will see that one in the next, after next sessions, how you're going to develop that. You can calculate this deformation. You need to be really mindful. You need to calculate this deformation in the central bridge, because you see when the bridge is expanding, these two are pushing, this joint will be closing. In here is opening up, this is closing. The creep shrinkage, the end at the abutment location, creep shrinkage is opening. That means shortening the length, opening in here, right? The shorten in the length in here, the opening as well. Is do the same way, but it's doubling up. So you need to calculate this joint length in a proper way, and then calculate what is the required gap. That gap actually dictated mostly by the size of your bucket you need to put to get the drainage. I already given you that details. If you go back to the lectures slides, and if you grab, if you don't have, if you can't find, you tell me, I can send you that detail. So then you can estimate the sphere, and then you have everything what you need for your concept. Then you can develop your sketch. Then you need to know the abutment. When we are going to do the abutment in this bridge, there are the abutment A and abutment B. The cheapest form of the, because you see your bridge is up in here, your ground is down there. You had to fill here, right? Otherwise, you had to build a massive retaining wall to hold this earth pressure, right? If you have a option to fill this one, it's much cheaper to fill here. A lot of excavated material, drilling, putting, excavation and everything, right? You have to bring material to build access road. You can reutilize those material to backfill in this area if it is allowed. But if you see the constraint in the abutment A in the front, we're going to build a slip road. You can't have a better abutment in here. You can't have a better here, build a road there. Therefore, you need to have a vertical face in your abutment. But in here, it's no problem. You can backfill. So you can have a better in abutment B. You need to have a vertical face. I explain it to you. The vertical face abutment, normally we use reinforced concrete wall or reinforced soil wall. You have seen the pictures I share with you in my previous sessions here. Then, how are you going to get the abutment dimensions? Again, abutment dimension, as I mentioned before, like the cross beam, they automatically dictate by the geometry itself. This end distance, that is 450, because you have a strip seal, not the strip seal, you have a, you're going to have a finger plate joined here. You need to have a drainage gutter there, that's gap, the thermal expansion contraction, right? Because this bridge is creeping away, then it's mostly governed by this bucket dimension. So then that gap plus thickness of the wing wall will dictate the width of this member. This member. You see, without doing a lot of calculation, a lot of numbers is come with the geometry. That is the reason I explain you so many information. Last 6 session, I feed you with so many information, explain it to you, provide it with so many pictures and give you a lot of information, because the people think brick design is the drawings online, do a model, do a calculation, get something and put some Rio. It's not going to work that way. Because when you make a bridge, it should be a bridge. All the elements need to be assembled, should be fitting. Yeah. Someone say, I want to make it economical. I want to push, I want to reduce this bit by 100. I will going to save this much of concrete in here. It's not going to work. Because most important thing is this water need to be collected and drained. Otherwise, every time rain, everything will be flood. This bearing will be underwater, soak. Yeah. These are the things you need to be mindful, because this dimension is come automatically. And like a thickness of this member, yeah, it's mainly governed by not only the sizes, it's the 4 layers of Rio plus the concrete, 4 layers of reinforcement plus the concrete cover, front and the back. Yeah, 4 N20 bars, so 2 layers of N24 bars and 2 layers of N20. That's already 40 plus 50, 90, plus cover 45, 45, both sides. You got a 90. You can see 90, 90, 180 is already in there. So that member you can reduce to optimum size 300. If you do 300, if you go to the top, you will have issues with getting this bracket and support and this one in here. This number 350 you can reduce to 300, but you can't reduce to 250. If you reduce to 250, you can't put your vibrator inside to vibrate the concrete. Yeah, remember that one. These dimensions in this bridge structures becoming massive is come with the designs and constructability and durability reasons. Yeah, these dimensions is come naturally. That's what I need to say. Yeah, when you get these sizes, geometries, sketches right, you can put this stuff in your model. You can calculate your reinforcement. If you are a smart design engineer, you can say, I just put minimum Rio considering the size of this beam. I use a strut tie model because it's a non-flexural member. I will get my Rio and I will use that one as a percentage. I'm going to use that one as a percentage and I will going to do my cost estimate. It's right, it's correct. Yeah. When you are selecting the bearing, you can either design or you can pick one. Normally this kind of a bridge is depend on the loading. In Australian environment, it's 380, 480 bearing. The thickness is 137 in average. Height will good enough for costing purposes. But otherwise, you can model this one, you can calculate and you can design your bearing. It's not a difficult things to do. Bearing design is very easy. Bearing is the flexible element designed for compression and the shear deformation. Here, thickness will govern by the shear deformation of the bearing. Area will govern by the compressive stress in the bearing. Yeah, it's very simple. The bearing compressive stress, if you could remember, is limited to 10 MPa. Yeah. And the better, all this material you're going to use for the filling, you can use the batter in the abutment B. And I say the piling in the abutment, we use minimum 900 diameter pile because this beam is quite long. You can space the pile in the long spacing because these members are quite large, right? So you can have even close to 7 meter spacing. Don't go beyond 7 meter, but some designs we push that one really hard. You can design, but a lot of still you can design. Yeah, but it's better. Yeah. Some we even go close to 8, 9 meters as well. This is, I give you like a general guidelines. If you would like to model this bridge by yourself. The other side, the abutment bay, we need to have this slip road, right? Because there is a valley and the slip road with this arrangement, they need to have a 7 meter. You can have a better here because there is a valley in here. You need to protect the vehicle going down in here. Another thing, you need to protect this one hitting on the abutment. To get the vertical face on the abutment, we use the RSW here. The reason I put this RSW in the front, you need to have a walkway in the front for the people to come and do the bearing inspection. You see this walkway? Because it's a better, it's no problem to have the walkway, but in your RSW, you need to have this walkway with the drop in here. That's why we need to push this RSW into the front. You have to push your abutment behind in here. So then your slip road is in here. Yeah. If you want to design this one without RSW, you can design with RC wall. Instead of having this one, you can have a reinforced concrete L-shaped wall in here. Yeah, but that wall need to get this earth pressure in here. Yeah, it's not that easy to, it's not that difficult to build as well because this pile is a space at 7 meters spacing. Yeah. And the abutment A, I put, because of the slip road, the better slope is not an option in from here. Because of that, it either reinforced concrete wall or reinforced soil wall should be provided in front of the abutment. Yeah. That's the bridge solution you got for the slab bridge type. This particular bridge we built with the Super T. This is the earliest stage. You can see it's the urbanized area. It's got the largest traffic volume in that motorway, the highest, that point. We work in the environment. You can see this slope, they were building around here. Actually, there was a creek. We're going to fix it. You can see this access road. It's the footing construction, the piling construction. They pour the pile. Yeah. You can see the construction staging. This is the column construction. You can see the people are working. It's not that simple. The formwork system, people are hiding up. You can see you need cherry pickers and other thing. You can see the formwork setting for headstock after constructing this. I want you to imagine the height of the people and this structure's height and this boom heights. And this is the cross set construction. You can see the lot of Rio. And after you can see finishing, these are, you remember this one, these are the lateral restraint blocks. Yeah, you can see the finished surface in here. And then this is the concreting of the headstock. Sorry. Responding really so, sorry. The headstock construction. You see, when they bring a girder, in your case, we have 156 girders. They have to fabricate in a yard. You need to go and store. You can see the Super T girder bridge. You can see the way they stock on top of each other. The stock top of each other. You can see this person here, the height there, because this girder 1.5 deep Super T we use in here, this 4.5 meters this height. You can see the way they transport. I put this picture for you to see. They use 2 trucks. The one in the front, you can see this is in the back. Yeah, this is front, you can see here, this is the back. You see how much coordination you need to transport them. The preparation you need to do. Yeah. They all cost. They all cost. This is the construction erection of the girder. You see your span, we measure on top of the girder. You measure your span on top of the girder, right? We measure the span on the top of the girder, but when you are erecting, your thickness of the girder is there. Therefore, the lifting of the girder is not easy. You see, when you are lifting the girder, you have to rotate the girder. It's like in a rectangle, we use the hypotenuse to put the stuff, go through that one, right? So you have to rotate the girder and you have to place it. You can see the bearing pad. I said the bearing, we need to make it horizontal. You see the bearing they place on here, they are lifting the girder to place in this one. This guy is the one, the project manager of this project. He's the guy, is the project engineer of this project during construction. We are the designers, but we are not there. Yeah, you can see the way they're placing. I just put this picture for you to see. You can see this height is about 15-20 meters above the ground. You can see this person to place this girder in the right position of the bearing. He just need to go here. This crane is lifting the girder up. The simple mistake is girder is more than 60 tons, will crush. Yeah. This is the engineering. I put these pictures for you to see these constructions, the working and the drawing. I explain you less than 2 hours time to develop one concept in this particular bridge. Yeah. Then one might can ask, we can design this bridge within 6 months. Why can't they build this one within 3 months? Yeah. You can't. Yeah. You can see they erect already one girder. They are lifting this one, they place in the second one. When you place the girder, they are butting up next to each other. Your bulky girder is the same. You agree with me? You need to put that girder in there, even Super T, you got a walking platform. When you are erecting girder, in the middle, this gap, we place the cover with the formwork. Then the walking platform is automatically formed when you erect the girder. Here, you can see this girder. So the cranes are in here. Some girder is already lifted. I just want you to imagine in your valley when you were designing and building this bridge exactly the same. So I would like you to develop this assignment by yourself, even the same one, and draw the sketches. If you can do by CAD, AutoCAD, develop this elevation and the cross sections and see how it looks like. You can see this urban design features. We get these member sizes, not only engineer, our structural engineering thinking, we combine with the urban designers, architect input, is give a good solutions. At the end of the day, when you build, construction is a bit difficult, but you get a better outcome. Then behind this one, I give you some guideline. If you're willing to use a different form of bridge, how to estimate the thickness of the depth of the girders, depending on the span. This is based on ASTO. Sometime you may have to change a little bit for Euro code and Australian standard, definitely. How to get the thickness of the slab between if you know the spacing of the girder for the simple span and continuous span bridges. Your bridge, please note that simple span, though your link slab is continuous, but your bridge is simply supported. Because of that, you have to go to this column. If you are interested to work on try out on a balanced cantilever bridge, you saw the Panankau bridge drawing, I explained it to you. I gave you information. The balanced cantilever bridge, yes, of course, it's the depth is higher at the pier. It's a continuous span bridge and it's less at the center. This is how you can calculate L over 16 to L over 20, the range for you to calculate your depth. at the pier and then at the span. You can have the span parabolic, or you can go flat, and you can go with like a trapezoidal shape, architectural precinct. I put you some example, the different forms they use. You can try out in this one. Just develop sketches for you to get yourself the what is the balance cantilever bridge look like, what is the single cell, the twin cell box looks like, the principle they're going to use in the strut tie model. I will draw some sketches and I will put in this this folder later on. You all can see different forms you can see in the bridges. Yeah, but I would like you to work out yourself. So this is the end of the presentation. Any questions? Anything, if you want me to explain some, if it is not clear, you want to know more, or any questions, so you can ask me, or please. No questions? May I ask a question? Yeah. Why did you use 1.2 meter deep super T, or 1.2 meter deep girders? Why didn't you use? I can see Sampath name on the, yeah, to me. Oh, Nadika and Sampath can answer me. I will help you. Anyone can answer. If I use a 1.2 deep girder with the slab thickness, we become composite. The depth is 1.4. Then the maximum span we can go is about 27 meters, right? The maximum span length is 27 meters. Because you saw in this environment, this girders is really difficult to transport, difficult to lift, all those things. Lighter the girder is easier. Then why didn't I use 1.2 meter girder with 25 meter span? Why didn't I use it? Can someone answer me? There's an obvious reason I can't use it. There's an obvious reason I can't use it. If you know the numbers, you can tell me easily. Because that's right. Yeah, that's right, Malik. The creek width is 30 meter. Your span is 28 meters. Then you can't put whatever span arrangement you go, there will be a pier within the creek. The span of the bridge always greater than the length width of the creek, 30 plus clearance requirement. The thickness of the column plus some spacing for foundation. That is another obvious reason. There's a standard practice in the construction 1.5 and 1.8. That is the cost differential we're going to look at in there. But in the reason to select that one, because if 1.5 meter girder, if you can span only 34 meters, you are really struggling to build this one, but still you can. Yeah, because your column width is only 1.5, still you can put the pier. You can design a very special footing. Yeah. There was a comment in there say we do not use drainage below expansion joint in Sri Lanka. I think if you are using a strip seal joint, you may not use the drainage, but if you are using a finger plate, you must use the drainage. But still you can go and retrofit that one, but it's very difficult. Yeah, there's a way to do that one. If someone want to do that, I can give a, I can give you a design to fit in that one. Yeah, to do that, but it's difficult, but a little bit expensive as well, because over here we use like a 6 millimeter or 6 millimeter thick plate and bend that one to get that shape, and they screw that one into the face of the abutment. Yeah. That is the reason we didn't use the 1.2 is not going to economical as well, because you have so many substructure. You are playing here between the optimizing this number of substructure, optimizing the number of substructure, and then optimizing the number of substructure again. The maximizing the girder span. That is a concept we are using, but in the main constraint in here dictate the span arrange the span selection as well. But please remember the 1.8 deeper kind of girders when you use for construction. I will go back to that slide before I finish this presentation today. Though you can go to the 11 girder one. Okay, this is the bit extreme end with 13 meter span with 1.5. Sometimes you get benefits out of it. It's all depend on the country to country, the way you're going to apply. Because this 1.8 deep girder construction in bridge, for example, in the Australia is not that common. The 1.5 is the quite common. Because of that, it's becoming a standard practice, then easy to adopt. So when you are selecting your bridge girder depth, you can always go select that one. Yeah. What is the standard common one you are using in your country? Yeah, because you can use any, you can fabricate any bridge, any girder, anything is okay. Then that will give a lot of opportunity for many contractors to when you go into market for bidding, it's more challenging because everyone can build it. If you propose a balanced cantilever bridge, segmental box girder bridge, yeah, you may not find a contractor to build that one. You need to bring from people from overseas to do that work. But if you design, the many contractors got a capability to build that, then if you go to market, you get a competitive price. When you present that one to your client, you can tell your client, that is one of the reasons I select this option. I think I didn't discuss specifically the dot point I put in the presentation. The dot point, the understanding construction requirement, I think quite obvious when you're looking at this picture. I don't want to explain you more detail. That's what I put a lot of pictures in here. And the associated risk, of course, the working in the height. And if there is a one risk, you design the bridge, but the girder can't be transported, right? There is some bridge, it's not allow you to get the 100 ton on the top. That could be a risk. Yeah. Another thing, you design a bridge, you come up with the segmental box girder bridge, you come up with the balanced cantilever bridge solution, but you don't have a contractor to build that one. You can recognize that one as a risk. Yeah. Another thing, the urban design features, you could see a lot of in your first presentation slide. I explained about the urban design beauties. So you can accommodate in your bridge design solution, because this bridge, we need to put the noise wall. I did mention those things in this one because my main objective is for you to come up with the bridge solution. That's the objective. Yeah. And please, please try this one yourself. And if you, if it is not clear, please let me know. I will explain it to you. Yeah. If you just want to talk to me, you can just, yeah, come on online and then can have a chat on Zoom or Teams. Yeah. Then if you do not have any questions, I'm going to see you guys next year, because the next week's next Friday onward, I'm on leave. And you all also having plans end of the year. Sometime on Friday, next Friday, you may have your Christmas party and your New Year party, or you may have other plans. So then I want to wish you all the Merry Christmas and Happy New Year. Please stay safe and enjoy your, I hope you're going to have some holidays. Enjoy your holidays and stay safe. That's more important. And wish you all the very best for your New Year's. And then see you on the New Year, because I think the next lecture I'm going to have it on bridge modeling. Sorry, I forgot to put the date in here, 17th January. Let me check that date again to confirm. Sorry, 14th Jan. Yeah, 14th Jan, because I'm going to work only 10th. We're going to have a 14th Jan. It's almost like a month later. We'll see you. Yeah. So then have a good night. Thank you.
Wish you the same, sir. Thank you very much.
Thank you.